All right, welcome back to the induction and recursion slides. Let's actually go to recursion now. So let us talk first about recursive definitions because that will lead to recursive programs, right? Recursion is just doing yourself inside of yourself. Okay, so let us define a set that is recursive. We'll call it BAL. This is going to be our first example. It's the set of balanced parentheses. So like this is a balanced parenthesis. Like these are balanced because like the first one closes the second one. These are balanced. This is also a balanced set of parentheses because like this one's closed. These two are also closed. That's totally fine. So it's just a bunch of strings that are all holding balanced parentheses. Hopefully that intuitively makes sense. And we can make it using recursion. We can have a base case and a recursive case, believe it or not. We'll first say that our base case, our basis for this set, is that lambda, the empty string. Just say that that's in the balanced set, because like what is the empty string but a string of balanced parentheses? There's just 0 there. So here's the set that we're building, right? We know that lambda, we're going to say that lambda's in the set for sure. And then the goal of a recursive definition is always like, if like take something from your set and make a bigger thing. Take something from your set and make a bigger thing. So like if x is in BAL, then take that x and put some parentheses around it. That's also in the balanced set. So that's showing that we can use lambda and this idea, this recursive rule, to wrap some parentheses around it and make it all work. And remember that just goes away to like lambda is the empty string. So lambda concatenated with some parentheses is just the parentheses themselves. And like we can use this one now. We have another one that we can use this recursive rule on and prove that this one must be in the set too. So it's like building up a set from the ground up recursively. It will become an infinite set, of course, right? And then there's also another rule. If you have two balanced parentheses strings, then their concatenation should also be a balanced parentheses strings. So put that in. If x is in BAL and y is in BAL, throw x concatenated with y in BAL. And of course they can have their chances being x and y, and so you have both sides of the same thing. Like use both of these now to put I don't know, this string in BAL. Okay? And that's how you build it up. You just keep on taking stuff that's already inside, running one of these recursive rules on it, or two things, right? That's it. If you just use these rules to define your set, then BAL, by definition, must contain nothing but balanced parentheses. You see how that's going to be the case? Think of any sequence of balanced parentheses. You can see how like this is made up of two of these guys, which must have been made with this rule, and so on and so forth, right? You can always bring it back down. But this is going to have a set of strings, and the strings are going to be every possible infinite kind of balanced parentheses. Isn't that fun? So that's a recursive definition. Again, there's like the same idea as using a recursive function. It's like you got a base case, a basis, like what's the smallest thing in your set, and then you have recursive rules, like given smaller things in your set, make bigger things. Recursively run those rules forever until the end of time. All right, so that's recursive definitions in a nutshell. Here's an example of them again. Let's make our own recursive definition this time. So let's give a recursive definition for the following subset S of binary strings, so strings containing ones and zeros. So in our special set S of binary strings, the string should be in it, a string x should be in it, if and only if x has this property. Okay? So our set must be the binary strings that have only this property. All right? So the set S consists of all the strings that have the same number of zeros and ones. Ooh, okay, so like 0, 1, 0 can't be in the set, but 0, 0 can be in the set. Oh, sorry. 0, 1, 0 can't be in the set, but 0, 1, 1, 0 can be in the set. Like same number of zeros and ones. Okay? So that's the set that we're trying to make. Here's how we can build it with a recursive rule, right? If you think about it long enough, like S has got to look something like this. It's got to be like, well, the empty string is totally fine. It has 0 zeros and 0 ones, so the empty binary string should be in there. You can't have just 0, you can't have just 1, because now they need a match, right? You can have 0, 1, and 1, 0, though. That's fine. So those are the kinds of things that should be added. So like our basis for this definition, like what's the smallest thing that's in this S set? It's going to be the empty string. That is a binary string that respects this definition. So lambda's an S. And then we need a couple recursive rules. We'll need more than one again. So here they are. Well, if we have something, if you can take something, right, if x is in S, then you can take that x and put a 0 on it and a 1 on it, can't you? Because that will keep the same number of zeros and ones, however many x had, right? Add 0x1 and also add 1x0. So you can wrap it around. The zeros and ones need to be both there, but they could be in any order. So that's kind of like lambda will make 0, 1 and 1, 0, because you can slap a lambda on in the middle there, right? So that's fine. Then like you could take this one and make 0, 0, 1, 1, and you could also use this rule and this idea to make 1, 0, 1, 0. See that? So those all exist. You got plenty of those. And then also, another way to make these, if you think about it, if x and y are both in S, then you could also add xy to S. Okay? That will also work. It's like if you have this guy and this guy, of course, if you slap them together, 1, 0, 1, 0, it better also be an S, because it's, of course, got the same number. Like this had the same number and this had the same number. They're all going to add to each other. Does that make sense? So now this will build this entire set, whatever it is, it's going to be infinite. This will build the binary strings that all have the same number of zeros and ones. All right. So each string has the same number of zeros as it has ones. I don't know if that makes a little bit of sense. It's like, all right, it's always in terms of smaller things. Here's a smaller thing, make a bigger thing. Here's a smaller thing, make a bigger thing. And that's recursive, because in recursion, though, you kind of think of it backwards. It's like if you have this one, it must have come from here, the smaller thing. But recursion, you can also think about as building up. All right, and that leads us, of course, to recursive algorithms. So a recursive algorithm, as we all know, is one that calls itself, right? It calls itself on smaller inputs, smaller input values. It needs to get down to some smallest thing. That is our base case, right? So each call that you make to yourself is called a recursive call. And the goal is, maybe, like I've tried to tell my students this, but it might not have made a lot of sense because I haven't taught them induction. But now that you're in this class and you know what induction means, this is why recursion kind of works. With induction, just like with induction, you get to assume that the smaller recursive call works. You just need to use its answer to build the final bigger answer, and it will be correct. And we can prove that with induction, okay? You get to assume the smaller recursive call works, so you don't have to expend any extra thought. Just assume that my smaller recursive call is always going to give back the right answer, all right? And so let's do the of course, classic example of factorial, where we're trying to compute the factorial of some number n, and the base case is like n is 0. 0 factorial, just define it to be 1, immediately return 1, and then the recursive case, right, n factorial is equal to n times n minus 1 factorial. And you can see this pretty clearly if like you write this out, like, let's see here, 5 factorial, that's equal to 5 times 4 times 3 times 2 times 1. And what is this but 4 factorial? So that's where that comes from. And then just like, what's the smallest factorial you can think of? It's 0 factorial. That's the smallest one that is defined still to be 1. You can't have negative factorials. Okay, so yeah, let me show why this works with just a little tree. And the goal is, though, eventually to be able to prove that it works without just hand-waving and drawing pictures, with actual proofs, right? So 5 factorial, let's say that we call our recursive case n equals 5. We run 5 factorial. It's not 0, so we skip the base case. We're going to go straight to the recursive case, and we're going to try and compute n times n minus 1, where n is 5. So we're going to try and compute 5 times 4 factorial. And again, this is going to like wait on the recursive call. This is going to go off and call 4 factorial. What is that? It'll hit the recursive case again and try and compute 4 times 3 factorial. And that'll also hit its recursive case, try to multiply 4 by this result. What is 3 factorial but 3 times 2 factorial? What is 2 but 2 times 1 factorial? Let me draw a 1 that looks like a better 1. And then what is 1 but 1 times 0 factorial? And now this is finally our base case. 0 factorial, let me give myself some room to write it, but 0 factorial is defined, right? We'll hit our base case, and it will give back 1. And so it'll this is now where the recursion unwinds. I've kind of like drew the stack backwards. So this is going to give back the 1 to whoever called it, and it was like waiting on the 0 factorial to multiply by its 1. It's like, all right, my final answer is this 1 times my 1, which is 1. And yeah, 1 factorial, of course, is 1. And so it gives back the 1 to whoever called it, which was this person trying to compute the factorial of 2. So it got back the 1 for 1 factorial. It can multiply its 2 in by that answer. So 2 times 1 is 2. And it can give that back to whoever called it. And that is, of course, the right answer for 2 factorial. And so this one is waiting on the 2 factorial to make its 3 factorial, to multiply that answer, the 2, by its 3 to make 6. And that's its answer that it will give back to whoever called it. And then this was waiting on 3 factorial. It got back the 6. It can multiply its 4 by that to make 24 and return that. And then this guy was waiting on the 4 factorial to make 5 factorial, to multiply its 5 by the 24. And it can give that back to whoever called it. And the answer is 120. And that's the final answer. Isn't that fun? So that is recursion in a nutshell. You try. So give a recursive algorithm that takes as an input a sequence of numbers. And have it return the minimum number in that sequence. All right? I want you to use recursion. So like take a vector, take an array, but I want you to go through it recursively. All right? A sequence of numbers, and gives back the minimum recursively, somehow. Okay? That's the idea. That's what I want you to do. And while you're thinking about it, I will connect to my starter code, or just code from class folder. Boop. This is lecture 21. Oops. All right. Did you figure it out? Recursive algorithm takes a sequence, takes a big thing, and returns the smallest thing in that list. So just say that like you could take a linked list, you could take a vector, but your input is a list of numbers, let's say. So like, let's pretend you're given a list. L. Let's think about this, right? Well, usually when you have some sequence, right, to work on, maybe you've done recursion on a linked list before, usually you recurse, right? You recurse on a smaller thing. Like if your input is a list, you're going to, well, what can you call that as a smaller list? Well, what can you call that the smaller thing? Well, it must be a smaller list. That's your only input, right? So usually you recurse on the length of the sequence. And that will totally apply here. So we're going to call this on a smaller sequence, all right? So let me use racket as an example, of course. So that's where I'm going to show you my answer. So let's say that our input list that we want to find the minimum is like the list 8, 6, 7, 5, 3, 0, 9. Can you see how you might recursively like chop off part of this list and make a smaller one? So usually it's like you split it like this. You have your first element, which is like your 8, and then you have the rest. This is a smaller list that you can recurse on, isn't it? And this is how you do the recursive case, right? The recursive case is going to be, right, call yourself. You can just get to assume that you'll find the minimum. You get to assume that your recursive call works. Assume that when you call it on this list, you're going to get back the 0. The answer given to you is the 0. And then your job is to compute the minimum of the giant list, the bigger list that had one more element. And so the one thing that you didn't consider was this first element. Like maybe it was 8, maybe it was -1. So the minimum depends on this. You're going to compare this to your first. Compare them both. And then the answer is the thing that you give back. The smaller one is the one that you give back for the whole thing, right? So the whole minimum now, using this recursive call's answer of 0, compare it with the 8, 0 is still smaller, so the minimum of the whole thing must have been 0, okay? That's the idea. So that is the recursive case. That's the algorithm. Recursive case. All right? You recursively find the minimum of the rest of the list. Min of rest You just get to assume that that's going to give you back the correct answer as long as you build up the final answer correctly. That's how recursion works. Then you compare with the one thing you haven't looked at yet. Compare with first. Okay? That's the idea. And then your base case is like, what's the smallest list, right? Because we're dealing with sequences and their size. What's the smallest list that I know the answer for, right? What's the minimum? I immediately know the answer. And if you think about it long enough, it's the list with just one element, right? Any element n, if that's the only thing on the list, the minimum must be n, yeah? So the base case is when the size of your list is equal to 1. That one element, the only thing there, is the smallest thing. Give it back, okay? So that's that example, and here is that in Racket. I will help you do it in C++ if you'd like, but I want to show you multiple languages. So here's this first one. Did I call this anywhere? I think I just wrote it. So it really will work. Let's see here. I think I can load this into Racket. But I can't remember how. I'll figure it out in a second. But here is the algorithm itself. So we're given, here's the name of the algorithm, minList. I'm just searching on my other computer to figure this out. How do I run it in interactive mode? So I say minList L, and just to print out like what's going on, I say like this, and this is where the actual work happens. We need to see if we're in the base case or the recursive case. Okay? That is what we do. And then here is our checks. Like if we're in the base case, that means the size of the list is 1, right? If 1 is equal to the length of L, then the only element, which is its first element, is the minimum. Give that back, all right? If L's length is 1. Otherwise, we're in the recursive case. L was bigger than 1, hopefully. And then we want to recursively find the minimum of the smaller list. That's this variable, minRest, to find that to be a min list of the rest. Okay, so that's that one. And then I use this minRest, compare that, right? Compare minRest, which is like the 0, to my first element. Compare first of L to minRest. If that one's smaller, return it. That's the real minimum. Otherwise, the min of the rest of the sequence must have been the minimum. Okay? That's the goal. And so now, I don't know. Let's just... No, I think I'd rather run it interactively. So let me say Racket like this, and I think, don't quote me on this, I think it's enter question or exclamation point, and then I give the name of the file. Recursion. Oops, recursion.racket. Oh yeah. So it seemed to work, and did I guess I did call it in some of these. Sorry. Okay, so let me comment out some of these. All right, if that's how I'm doing it, in that case, let's just do it like this. Display line, a call to like min list, and here's my list. 8675309. Whee! So here is, I probably have to make this smaller. And so I'm nice enough to print out what's happening. So when I call it, right? When I call it, I am just saying that I'm calling it here. So you're kind of seeing the stack. And so it's like calling this min list, which is going to split it off into the first and the rest. And so now it has to go off and recursively compute the rest, and so on and so forth until it gets down to the base case, right? And then it starts unwinding. It's like, all right, the minimum of 9, the list 9 is just the number 9. Give it back. The minimum of 0 and 9 now, though, is going to be the 0, and it's just going to stay 0. It's always going to be in the rest from then onwards, right? So it just keeps giving back min rest. And so that's the answer for that one. Any questions about that, please yell at me. Oops, not that one, but this one. So that's that idea. Let's keep going, and let's talk about induction now, because induction and recursion are tightly linked, all right? Hopefully you've seen their similarities. You can use induction to prove that your recursive stuff is correct, all right? So I kind of did this like a bit hand-wavy when I gave you previous inductive proofs, but just like you're recursing on something, you're always inducting on something. Like that's your predicate. That's the n inside of the predicate, okay? When you're doing induction, you must always specify the number that you're inducting on, because it's always about natural numbers, or some number that has the smallest thing and gets bigger, right? There's always some number that you're inducting on that's eventually getting bigger, right? So even though we don't write it anymore, there's always a predicate behind us, right, that involves the number, and that's the number that we say we're inducting on, okay? That's the idea. So for recursive algorithms, here's the hint for proving them correct. Always do induction on the thing that's getting smaller in each recursive call. So for example, the thing that's getting smaller in this algorithm is the size of the list. So you do induction on the size of the list. That is going to be how we prove this correct, all right? So let's do it. Let's prove that factorial, this recursive factorial function, correctly computes factorial, all right? So what gets smaller with each recursive call? You have to compute factorial of n minus 1, right? That's the smaller call. The number itself is getting smaller. So we're going to do induction. We're going to prove this by induction on the input n, all right? So essentially, again, there's always a predicate behind this, and the predicate is going to be that factorial of n is equal to n factorial. It always gives back the correct mathematical definition of factorial, okay? So here is how you write an inductive proof about this algorithm to prove it correct. So proof. Then we say by induction on n, if you want to be fancy. By induction on n. And now, here's what we do. Like, we're inducting on n, which is the parameter to this function. So what could we have been given? Base case. Input precondition, it's non-negative. So the smallest number is 0. So base case, our n was 0. All right. We have to prove that this all runs correctly and gives back the right answer for 0 factorial, right? Because it's supposed to be computing 0 factorial if n is 0. So we're going to hit the if statement, right? If n is 0, return 1. Sure, yeah, that's the right answer. So we have to show that, hey, is 0 factorial equal to the 1 that this function's returning? And of course it is. So we can just QED on that one. That checks out. There we go. So the base case is proven. And now here's how you prove the inductive step, which shows that this works for every number. So our first beefy algorithm proof, inductive step. Well, okay, what we're doing is we're assuming P of k implies P of k plus 1, right? Which means assume factorial of k gives back the right answer. Prove then, using that factorial of k plus 1 gives back the right answer, right? So here's the breakdown. Assume that the smaller call works. And this is why you get to assume that when you're writing your inductive programs, just kind of like you have induction in the back of your mind. So you get to assume P of k, right? Then what you do is prove the original call is correct for the bigger element, k plus 1. Prove the original call is correct. And that is P of k plus 1. Okay? So here we go. So if it was not this case, right? If we're not in the base case, n must be greater than or equal to 0. And so that means we're hitting this line right here, always. And then returning something times that answer. Let me erase here. Okay, so n is greater than 0, we know that. By our inductive hypothesis, right, we're going to run this line. Oh, sorry, not this line. We're going to run this line and set r to be the factorial of n minus 1, which is a smaller call, right? By h, ih, like, I don't know, our smaller call, which is n minus 1 here, just think it like it's the number k or something. By the inductive hypothesis, r must hold, right? This is computing factorial of n minus 1, that's smaller than our number. R must hold by the inductive hypothesis, the real true factorial of n minus 1. That is the goal, all right? What we need to show is that in this case, we're returning the true answer for the original n. We need to show we return the real n factorial. So I'm kind of like switching up between k and n. It's like, it's really called n up here. It's easier to talk about it that way. This is clearly a smaller number, though. We get to use our inductive hypothesis on it, just like k and k plus 1. So what we return then, we return r times n. That's exactly what we're returning. We get to assume that math works in our programming language. What's that equal to, though? We get to assume, right, based on our inductive hypothesis, that r is equal to n minus 1 factorial, and we're adding another n on that. What is that but n factorial? QED. So we've shown in our inductive step that assuming this call works out, which we get to do, right, it's a smaller call, the true answer is returned. QED for the whole thing. We've just proven that factorial correctly computes the factorial for any non-negative integer n. Isn't that beautiful? Isn't that lovely? That is such a powerful idea. Okay, so let's keep on going. More examples. All right, so here is another program. It is called reverse string, and here is what it does. It, let's see. What it does is it reverses a string. It takes a string s and it gives back its reversal, and it's going to split it up into, like, if it's not the empty string, it's going to split it up in terms of like the first character in the string and the rest of the string. So very similar to how we broke down a sequence. There. So for example, like if we're giving it ABC as our string and we're asking it to reverse it, then what's going to go on in this function is, well, it's not empty, let C be the first character in S. It's going to like split this up into A and then BC, and that's going to recursively call, like this is how we think about it when we're implementing it as well. It's going to recursively call reverse on this smaller string, right? Reverse string after it removes the first character. And so that we get to assume, right, is going to give back CB, or we're going to prove that it's going to work out and give back CB. And then we're going to shove this character at the end of it, okay? Added to the end. And so that's going to be, we put this A right here, and then we give back CBA. And that's the reversal, okay? So we're going to prove that this is correct. Again, we have to have something. We have to have some number that we're inducting on, and it's going to be the length of the string, right? Because every time we call it, it's going to be on a smaller string inside of here in our recursive calls. So here's how it works. So if S is the empty string, return just S, all right? So the base case, that's the base case. And that's going to be the base case of the induction and the recursion. So the base case, if the length of S is equal to 0, it's the empty string, right? That means S is the empty string. And we're inducting on this number, right? So that's what gives us the emptiness. And return S, well, the empty string reversed is still the empty string, so that all works out. Base case is fine. Now we have our inductive step. What do we do? Well, that means S is equal to some bigger string. It's got at least one character at the start. Let's call that A. S is equal to A concatenated with some smaller string R. Could be empty, though. So in this algorithm, it's like let C be the first character in S. So C is equal to that A, and then remove C from S. So that means set S to be R now before we run these lines. And now S prime equals reverse string on S. So S prime, this variable, is going to hold, right? We get to assume by the inductive hypothesis that it's going to hold because this is a smaller string, right? When we're doing induction on the length of the string, we get to assume that this recursive call works. That's what induction gives us. S prime must be R reversed, and I'll draw it like this, like R with a backwards arrow. S must hold R reversed by, and we get that fact, right? We know that that must be true by the inductive hypothesis. That's a smaller call, okay, on a smaller number. And then, all right, what do we do with that? We're going to compute some number S, some string S to return. That is S prime, which is reversed R, with that C added to the end of it. Concatenate with that with C, which is equal to that A that we had before, so it's equal to R reversed. Concatenated with the A, for example, that we're calling this first character. And that is going to be like, well, here's this first start of the string backwards. It must have gone at the end. And then this is the rest of the string backwards. That is the correct order. That is a correctly reversed string. And so that, we've just proven that for any string, reverse string reverses it. Does that make sense? The recursive call is on a smaller thing, and so by the inductive hypothesis, we get to assume that it's going to work out, and we just need to use that to prove that the final answer that we give back, which is this S, is the correct thing, which is the reverse string in this case. All right, I hope that makes a bit of sense, a bit more sense as I keep giving examples. So that is the idea. All right, so here is my min list function that I just showed you. Here it is, and here's an example of it running. I would like you to prove that this algorithm to compute the minimum of this sequence gives back the correct value for every non-empty sequence of numbers. And as a hint, your inductive step should have 2 cases. So give that a try. And it's all about non-empty sequences. So what's the smallest one that's going to work out? What must be your base case? Doing induction on the size of the list, 1 is the base case. It all matches up. So here is how I would prove it. Base case is that the length of our sequence is 1, and then you just give back the only element that is by definition the minimum. That's what the algorithm's doing. That is the only number in there. It's, of course, the minimum of everything. It is everything. Inductive step. That's when the length of L is greater than 1, and that means we go to this else case. So this is our recursive case, right? And so what does it mean when the length of L is greater than 1? Then, okay, L is big, it can be split, right? Which means L has at least 2 elements. It can be split into a first and a rest that is non-empty. All right, a rest that is non-empty that you can then call yourself on. That's the goal. Okay. And then we're going to define min rest as the min list of that rest, of the smaller sequence. Because it's a smaller sequence, by the inductive hypothesis, we get to assume that min rest, that variable, is going to hold the correct min of the rest of the list. Assume min rest correctly holds the min of the rest. Okay. And then here's where the 2 cases come into play. That you're going to have to hit both of these sides of the if statement because you're not sure which one's true. You're proving that it's true always, right? So you have 2 cases. Either the first number is less than the min rest, or the first number is greater than or equal to the min rest. That's your if body and the else body, yeah? So these are your 2 cases. These are what they must be to prove that the entire algorithm is correct. So case 1 is assume that you're in this case. If first is less than min rest, well, if we're assuming that min rest is the min of the rest of the list, and first is smaller than even that, then first must have been smaller than everything, all right? And so we're going to return first in that case, and that is the correct min. That checks out. Case 2. If that wasn't true, if we hit the else case, it must have been that first was greater than or equal to min rest, right? That's the opposite of that. If that's true, we're going to return min rest. And of course, that is a smaller value than first. And so it must have been the minimum of the whole thing. Checks out. QED. This was a correct algorithm. Okay? Please yell at me if you have any questions about that. That is the idea, though. All right? So that's recursive correctness, recursive function correctness proofs. Let's also talk about time complexity analysis for recursive algorithms, right? Got a lot to talk about. So the time complexity of an algorithm, right? It's just a number. It's like how many basic operations is this function going to do? And so you can think of it as a function, even though your algorithm probably is its own function. You can think of the time complexity of a function, or of some algorithm, as like T of n, that calculates the number of basic operations performed by that algorithm on some input of size n, for example. Okay? Again, there's a notion of size of a number, because things are getting smaller in recursion, right? In recursive calls, something's getting smaller. So for a recursive algorithm, T of n is going to be defined in terms of itself, because like the time of me is the time of my smaller call plus some extra work. It's going to be using a recurrence relation, so it's going to appear inside of itself. Like, I don't know, T of n, this time for this call on n is equal to one basic operation plus the work of doing a call to n minus 1. So that's that amount of time, right? It's in terms of me. And so once you have these kinds of recurrence relations going on, to analyze those, you're going to solve it. I'm going to show you how to solve these recurrence relations that exists, right? So to come full circle, if you want to figure out the time complexity of your recursive algorithm, you need to make a recurrence relation for the number of operations on it, and then solve it, okay? So for example, let's come up with the recurrence relation for factorial, all right? And I'll show you how to solve it as well. So factorial, it's not too hard, right? So in factorial, in the recursive case, right, if you're like the number of steps for recursive factorial is in the recursive case, where is it? Oh no, hopefully you can still hear me. My PowerPoint's being very slow right now. But there it is. It's essentially, oh gosh, hopefully the computer's still happy. Here is the recursive case of factorial. It's going to be n times n minus 1 factorial. There it goes. And, well, this is a recursive call, so that's t of n minus 1 plus one extra piece of work, right? One step of work to multiply n by it. That's the recursive case. That's the amount of time it's going to take. It's like, all right, it's going to be like call yourself factorial of n minus 1. That takes that amount of time. And then multiply it with your n. That's going to be like one basic operation. So that is the time complexity of factorial. All right? And then I'll show you how to solve it in just a second. But to get there, let's talk about this idea of divide and conquer algorithms. Okay? So divide and conquer algorithm, I think I taught this in 41. If you did not hear about this in 41, it's not too hard. A divide and conquer algorithm is one that solves a problem recursively by taking some input, right, its original input, whatever it was, and it breaks it down into smaller subproblems that are about the same size. So like, I don't know, you have some big sequence that you're working on. If you hand that off to a divide and conquer algorithm, what it does is like it splits it in half, and it's going to call it on a half the size input twice. That's the goal. You can also split it into like 4s and 3s. Divide and conquer just splits it essentially into a bunch of smaller subproblems of roughly the same size. It doesn't have to be by 2 though, but usually in computer science you're dividing by 2. Okay, so yeah, here's an example in Racket that is binary search, which I don't tend to believe this is actually divide and conquer because it forgets about the other half, but your book thinks it's divide and conquer, so why not? So let me show you a divide and conquer algorithm that is binary search. So here's what binary search is all about. I'll comment out this one. And so let's say that what is binary search, right? You have some vector, v, and some value, vector or array. Let's say we have a vector v and we have some value that we're searching for in that thing, okay? This is going to be essentially it turns into a recursive algorithm if you think about it enough. There's always a concept of where you are, right? So binary search is, all right, if I'm looking for some value, compare it to the middle, and then like if even that's too big, maybe I need to go left, right? And now I have half the size, even less than half the size sequence to search through. And then I'll look at the middle of that and figure out, all right, did I need to go left or right? How does it compare? And you're always chopping off half the sequence every time. Maybe you need to go right that time. And so on and so forth, forever and ever and ever. That's how binary search works. It's always look at the middle of your current subarray. And we'll keep track of that. This is going to call a helper function. That's like, all right, my subarray that I'm looking through at the beginning, it's like every index between 0 and the length minus 1. Look for the value between this start index and this ending index. So that's the recursive version of binary search, all right? It's like between 0 and n minus 1 to start, because I'm not sure where it is. And then look in the middle of that. Look in the middle of that. So, oops. And the middle is going to be start plus end over 2, essentially. This is start plus end over 2. That's the middle index. The middle value is just go there. We say vector ref in Racket to go somewhere in a vector. They also have vectors. And so look at the middle of your current subarray. If it was what you wanted, right? You found it. If you found it, just give back that index. Otherwise, you're supposed to give back the index of where you found it, right? If it was what you're looking for, you're done. If there's no array to search through, right? If it's an empty array, you didn't find what you were searching for, so that's like the base case as well. -1 is like if the search space is empty, the start is greater than the end, for example, if they passed each other. Then, otherwise, like if what you're looking for is smaller than what you see, then you have to search through the left half. What does that mean? it's a smaller sequence, isn't it? It is recursive. So if the value that you see, if this value that you're searching for is smaller than the middle value of your sequence right now, of your subsequence, then search in between that. Go between the start index and the mid index minus 1. That's the left side. Otherwise, if it's greater, the value that you're looking for is bigger than what you see in the middle of your current subsequence, search in the right half of that. So search between mid plus 1 to the end. See that? So that's how you cut off half of the vector each time. And then obviously, if it's neither of those, if it's neither less than or greater than, it must have been equal to, and we're trying to give back the index, and that means we found it in the middle. Return mid index because val is equal to mid. If you don't find something, like you end up giving back an empty search space, like search between indices 3 and 2, where 3 is supposed to be the smaller index. That just means it's not there, and so you return -1 in that case. And that is a recursive algorithm. Do you see how it's calling itself on a smaller subsequence? It's representing that with a starting index and an ending index. Okay? Searches v for val between start index and end index. That is binary search, and let me show it to you. Looking for something that's there, like 4. It's like, all right, I'm going to search between indices 0 and 4 of this giant vector. And then, all right, that means I'll search 3. Oh, 3 is not what I'm looking for. Let's go between 4 and 5 then, indices 3 and 4. And then it just so happens that the midpoint of that is going to be the smaller one. It's going to immediately find at the middle index what I wanted, which is going to be the number 3. Isn't that fun? So that is the idea. That is binary search in a nutshell. Eventually, if you're looking for, let's say, let's do -4. If you're looking for something that's not there, it's going to again be like, all right, it must have been, well, smaller than 3, so look in the left half between 0 and 1. That's what it's saying there. Between 0 and 1. Well, it's still smaller than the midpoint of that, which is 1, so search between indices 0 and -1, which of course don't exist. And so that's when you know this is an empty search space now. 0 is supposed to be smaller than -1. It gives back -1. All right, so that's binary search. Here's its recursive way of doing it. You just call it with starting index 0, ending index size -1. All right, so that's an example of a divide and conquer algorithm, but there are many others. One is called merge sort. It's a sorting algorithm that is really divide and conquer. It's really dividing into separate halves and actually using both halves. This is the one that I think is true divide and conquer. And let's talk about the analysis of it. It's going to be something like this, where it's like, this is the time that it takes to do this one. We have to we have to relate t of n over 2 and another copy of t of n over 2. Like somehow we need to analyze that, okay? So let's do merge sort, and I'll show you how to analyze it as well. So this one is really divide and conquer. This is supposed to sort a sequence, okay? What you do is like, here's our sequence. Let's say that's completely unsorted. 4, 3, 2, 1. Merge sort is, if you didn't read about it in 41 or something, I think it has it in your book as well, so try and read about it. But here is the idea of merge sort. Or let's say it's 4, 2, 3, 1, just to make it more interesting for us. Completely out of order. So like you give it a sequence and it's supposed to sort it, and it does it in a divide and conquer style. So it's going to split this up into 2 subsequences. One's the 4, 2. One's the 3, 1. And then it's going to recursively sort that. Right? So recursively, it's a smaller list. Assume it does it right. Assume that this is going to give you back the list 2, 4. Assume that this gives you back the list 1, 3. Or the vector, whatever you do. And then there's one last piece of the puzzle. It's like, take this and this. They're now sorted. There is an algorithm that you can come up with that merges those 2 sorted lists back together. It's called the merge part of merge sort. So it's like, you just put pointers at the beginning, like, how does 1 and 2 compare? Well, 1's smaller. All right, I'll take the 1. I'll put that in my next list. Okay, now I have 2 and 3. Which one's smaller? Okay, 2. I'll bring the 2 in. Now I'm comparing 3 and 4. Which one's smaller? I'll take the 3. And then, well, I'm done with this one. I must take the rest of this one. So bring in the 4. And so that's a nice algorithm to put it back in, all right, to merge it back. So that's merge sort in a nutshell. Divide every array in half, or your list, whatever it's called, recursively sort each half, and then merge the two sorted arrays into one bigger sorted array of the original size. Okay, that's the idea. So that is merge sort. Let me show you that in Racket. Here it is. So merge sort is made up of two pieces. You got merge sort itself, which is like, I'm sorting this list L, give back the sorted version. And then there's also a merge algorithm that takes two small sorted lists, sorted sublists, and merges them back together. Okay? So let me just prove that it works to you. Merge sort, and then I'll give it the list. 4, 3, 4, 2, 3, 1. It really will work out. Oh, did I unfortunately miss something? Oh, sorry, forgot a closing brace there. And so, if you think about it, it's like calling merge sort, calling merge. I'll go through this one quickly. I want you to study this on your own if you haven't seen it before. But yeah, essentially merge sort is, all right, I need to make two halves of my array. So either it's already empty, like the thing I'm trying to sort, the base case is if it's empty or it's size 1, it's already sorted. So just give it back. Otherwise, it's at least 2. And so let's split into a left half and right half, sort them recursively, and then merge them after they're sorted. So merge is kind of slightly complicated. It takes two sorted things and makes a bigger sorted list. And so if either of them are empty, that's like your base cases. Otherwise, if they're both non-empty, just keep on taking the smallest thing from each and then pack those into some final list. And you can do that recursively. All right, so that's the goal. I don't really care too much about teaching it to you because you'll read about it if you haven't already. But let's analyze it. So what's the effort of dividing something in half, right? Divide an array in half. Well, that's going to take some time, right? You're going to have to like make n over 2 elements here, like n over 2 process, n over 2 process. That's n work, right? Theta of n. I have to put each element somewhere, either in the left list or the right list. That is linear time work. Okay? That is theta of n, let's say. And then I have to recursively sort each half. I have no clue how much time that takes, but I'll just assume I have some recurrence for it. And I'm going to call it on a half the size list. So recursively sorting each half is 2 times n over 2. And then merging two smaller arrays into one bigger array is essentially just iterating through this one and this one, visiting each element and adding them. So it's going to be another linear time thing. All right. So this is the kind of thing that we need to solve now. Like I know how much time it takes to do the smaller pieces. I want to solve for t of n though. That is going to be our goal. So let me show you how to solve these recurrence relations. So solving recurrences with trees. Here we go. So we'll do it for merge sort. We'll do it for all of these guys. So first of all, what is the recurrence for factorial? Remember that one? That was t of n equals. Well, you got to make a recursive call and then multiply that answer by what you get back. So that's t of n minus 1 work plus some constant amount of work. Okay? That's going to be our idea. And then also, like, in your base case, t of 0 is going to be constant time. Just immediately give back the number 1. Okay? So we can solve this. Okay? If you think about this long enough, it's going to be, all right, what is t of n? It's going to be, well, I have to do constant work right now, and then I have to make a recursive call to t of n minus 1. So it's going to be whatever this is plus whatever this is, right? And so, again, at t of n minus 1, I have to do constant work, so one basic operation essentially, and then do another smaller problem. So this better call t of n minus 2. This is essentially a tree way to think about it. Like that's going to do at t minus n minus 2, it's going to do one piece of work. That's going to also call off to t of n minus 3, which is going to itself do one piece of work. And then all the way down, we're going to keep on asking for all these things, and we're going to go to t of 2, right? That's going to take one thing, plus whatever t of 1 took, which is another recurrence. Another call to our recurrence. T of 1 is going to take 1. T of 0 is going to take 1 piece of effort to do. And like, these keep calling each other, right? The total time for t of n is all of these summed together. So how many 1s do we have? Well, it's of height n plus 1, I guess. Height is essentially n. Height is 1. All right, let me write that better. GHT is 1. And so, well, I'm doing the solution then is I am doing n times constant work. Therefore, the algorithm is linear. That's how you solve it. See that? All right, binary search. What is its time complexity? Well, in the base case, of course, if you have an empty empty sequence to search through, then it's constant time. And then at any other case, when you have a sequence, a size that is not 0 sequence to search through for your binary search, whatever you're looking for, it's going to be, all right, I need to call myself on a half the size, t of n over 2 input, whatever that time it takes. And then I also need to do like some comparisons, return an answer. So it's going to be some constant work after that as well. All right, so we can solve that with trees as well. So t of n equals t of n over 2 plus constant work at each level. And then also once you get down to 0, we know that the answer is constant. So let's solve that. All right, I'm trying to figure out what the time complexity of n is. How many basic operations? Well, it's going to take, at this level, constant work, and then I'll also add into whatever t of n over 2, however much time that took. And what is this but constant work at its level plus another over 2. So this will call t of n over 4 when n is n over 2. So it's that plus whatever this is, right? And what is this but, constant work plus its smaller one. Constant work plus a call to n over 8 work, which will do constant work at its level. And eventually it'll get down, right, to eventually t of 0, using integer division at least. And so, what is happening here? Well, we're doing constant work, but how many times? How many levels are there here? And if you think about this long enough, well, if you count all these, how many times can you have a number and still have something left? The answer is it's proportional to the log of that number, the log base 2. So there's log base 2 of n levels. And that is all we need. So that's log base 2 of n times constant work at each level. Therefore, this whole answer, the final one is going to be, this is going to be theta of log base 2 of n work. That's the time complexity of binary search. Hopefully that makes enough sense. And then finally, merge sort. What's the recurrence for its complexity? That's going to be t of n is equal to, now I have to call myself twice, t of n over 2 times 2. Well, let me give myself some room for that. 2 times t of n over 2. And then I also, at each level, I have some extra work to do, right? I have to do some halving and then merging. That's both going to take linear time, so that's just 2n, so it's still n, plus theta of n work after that. And then once I get down to the base case, like a size 0 list is already sorted, and just give it back. That's constant time. Okay, so that's the new recurrence. That's the most complicated one that we'll solve now, using this tree method. T of n is equal to 2 times t of n over 2 plus theta of n. All right, so I start this off like, what is t of n? At its own level, it needs to do theta of n work, and then it needs to pass off 2 t of n over 2 works. Okay, that's the goal. So it needs to do that, and then it also needs to add that to, well, something of t of n over 2, but twice. So I'll write one here and one here. That's how I'll draw it. So at each level, right, it's going to take, this is going to take theta of whatever this number is, so theta of n over 2 work. And this will take n over 2 work. Probably I shouldn't be using theta here, but you get the idea. And then these both are going to call themselves, right? They're recursive, so they're going to call each other twice. 2 n over 2 work. When n is n over 2, this becomes n over 4, right? T of n over 4. Now this is doing theta of n over 4 work. This is doing more n over 4 work, n over 4 work, n over 4 work. It's probably better to not use the theta, actually. And so these will keep on multiplying, won't they? Until I get down to ... all the way to t of 0. And I don't know how many times I got called, right? Eventually I'll get down to a bunch of t of 0s, and I know that once I get there, they're all constant at the bottom there. So it kind of doesn't even count. So like that's theta of 1, that's theta of 1, that's theta of 1. As many times as I need to. It's going to be a lot. What is true? Like we need to add all this up, right? This up with this, these, add these, add these. There's a pattern though. Do you see the pattern? Let me move all these over a little bit. Oh, it was not happy about doing that. All right. So what is true, right? At each level, if you think about it, like this is theta of n work. This is n over 2 plus n over 2 work, which is theta of n work. This is 4 times n over 4 work. That's again theta of n work. Ooh, do you see the pattern? And then finally, this is constant work, but how many times? Well, you need to go down until you have only one element in the list. And so it's going to be just for every element you have a base case. And so that's n elements. So that's constant work times n. So that's again theta of n. Do you see that? That's the idea. And again, we have log base 2 of n levels because we're halving each time. So log base 2 of n levels. And we're doing linear work, theta of n work at each level if you add it up. Which means the time complexity for merge sort is, well, there's log base 2 of n levels, linear work at each level. The answer is theta of n log n. That is the running time of merge sort. It's an efficient algorithm. That's a very good sorting algorithm. All right, please yell at me if that did not make enough sense. That's the kind of patterns that you'll look for when you're solving these recurrence is for time complexity. All right, I want you to try this one. Give the recurrence relation to describe the time complexity of this min list, minimum of a sequence algorithm. Do you see it? So the base case is pretty easy. It's like when the length is 1, for example, when the number that's inside of this that drives the amount of work to do is 1, then you just give back the first element of the list. That's constant work. But then for an arbitrary number, what is the time complexity? What's the recurrence relation? It's going to be, well, I have to call myself, right, on a smaller list, one smaller list. So it's the minimum of a one smaller list. That's going to take t of n minus 1 time. And then the rest of the work is just like do an if statement and return some stuff that's constant work. So that's just a bunch of extra constant time stuff. So that's going to be our recurrence, and that is exactly the same as factorial, so that we know that is going to be a linear algorithm, which makes sense. Just look at every element, find the minimum. Hope that's cool. That's a very nice way to think about things. And I have one last question about this topic for you. So give me a recurrence relation for this idea. This is not find min now, it's find max. It does it in a weird way. It's a divide and conquer algorithm. It's a little silly in the way it's doing things, but here it is. It's called find max. It's given a sequence and its size. Return the maximum element. It's trying to find the maximum element in the sequence. And I'd like you to give a recurrence relation that talks about the number of operations that are performed on a list with n items. It's trying to find the minimum of a list with n things in it. All right. So there is a base case, right? This is the base case. I can give that to you. T of when n is 1, it's just return a of 1. That's a constant time thing to do to look up the value there. So that's 1. But now, what is t of n for some arbitrary n? It's like, what is the rest of this? Remember when your recursive calls happen, it's like, these are going to take t of whatever the size is. What is the size is the question. All right. So what it's doing is it's splitting off the list into halves. This is an A of m, that's the first half, m plus 1 to n, that's the second half. So these lists are essentially of n over 2 size, like maybe one's bigger and the other's like one smaller, it's not a big deal. But you can assume that this max call is going to take t of n over 2 time. So it's a one smaller list because it's on list 1, which is half the size as the original. And then same with max 2. List 2 is essentially half the size of the original. So we're doing a recursive call twice on half the size, and then plus how much work are we doing inside of this, like setting variables, if statements again, returning if one's bigger than the other. So that's just constant work, essentially 1, let's say. That's going to be your algorithm, and that is the same as binary search. So that's going to be, even though this is a very weird way of doing it, it ends up being essentially linear time again. All right, and if you don't like drawing the trees, there is an easier way. I have to show you the hard way before the easier way, though. This will work for most things. It's called the master theorem because it gives you one just table to look at, and you can finally get the answer for anything. So a lot of recursive algorithms have a recurrence that looks like this. T of n is equal to some constant times t of n over some thing that you're dividing it by, plus some n to the something work. Maybe that's a 0, so it's constant work, right? Or like n work or n squared work at each level. So there's a cool little trick that smart people figured out to solve every recurrence that looks like this, right? So for example, with merge sort and binary search, let me just steal these again. If it wants to copy, that is. Nice. So for merge sort, I don't really need the base cases right now. Watch. It's very nice. It's beautiful. So for merge sort, we have, well, let's see here. Oh, I did it backwards, excuse me. All right, I now regret copying this. This was merge sort. This was binary search. I guess it's not much faster than writing it at this point. Sorry. All right, for merge sort, what in the world do we got going on? What is A? What is A? What is B? What is D? So, oops. A is 2. B is 2 as well. And then D is 1. D is equal to 1. All right. So we can use this master theorem to give just immediately the answer. D equals 1. So is A less than B to the D? B to the D is exactly what? Is exactly 2. So A is 2 and B to the D is also 2 to the 1. So they're equal. So in this case, if A is equal to B to the D, then T of n is equal to theta of n to the D, which is 1, so it's just n, times log of n. Immediately we get the answer. Isn't that funny? Then binary search, A is 1, B is 2, and D is 0, right? Because it's 1. N to the 0 is going to be our 1. And so this, it's going to show us, all right, what is A? That's 1. B to the D is also 1. 2 to the 0 is 1. So again, we're in this middle case. And we get n to the D, n to the 0, which is just 1, times log of n. So 1 times log of n is just log of n. And so immediately, you can just read it off and you get the answer. Isn't that fun? So with that in mind, you try. Give all these, use the master theorem to just quickly give back the answer. Nice, and this will be the last thing for the day. All right, so let me just go through each of these. A equals what? B equals what? And D equals what? You have to write that down a few times. So I'll just do them all. This is 2, 2, 7, 7, 3, 3, 4, 4. D is 1, 0, 2, 1, I think. All right, so now I can use the master theorem. So it's always A and B to the D. So A is smaller than B to the D here. So we get the first one. So it's theta of n to the D, theta of n. This one is 3 to the 0 is 1, so 2 is greater than 1, so we're in this case. And that's an interesting looking one. If a is greater than b to the d, then t of n is equal to theta of, this is a weird algorithm that works like this. It's equal to n to the d, which is 0, so that's just 1 times. Oh, sorry, we're in this one anyway. It's n to the log base b, log base 3, because it's dividing by 3, that kind of makes sense, of a, of 2. And that's just a constant. That's some number. It's a weird power, essentially. Isn't that interesting? All right. And then this one, we have 7, and then 4 squared is 16. So we're in this first case, I think. And so that's n squared. It's always about like which one wins, I guess. It's like, is a winning or is b to the d winning? If so, like the logarithms come into play, otherwise n comes into play. That's kind of how you prove this, I would think. And then we have a, and then 4 to the 1 is smaller. So we're in this case where the second thing is smaller than the first. And so that one is going to be theta of n to the log base b, log base 4, because you're going 4 times, of a, which is 7, which is again just a number. You can calculate whatever that is, and that's n to some weird fraction. Okay, that is going to be our answers. That's the master method. That will let you solve for recurrences as much as you would like. All right, so please yell at me if you have any questions about this stuff. There's a lot to talk about, but that in a nutshell is induction and recursion. And so I think that's it for the week. There's no lab assigned this week. So yeah, ask me questions if you have any, and I will see you next time.